Hey guys, welcome back to Chem 20. Today we're going to be talking about a couple things split across a couple of videos. This is going to be a shorter video, and the next one's going to be about something called net ionic equations. They are easy. Honestly, you're going to have a very easy time with them, but we're going to do a number of examples just to make sure that we know what we're doing. That's not the topic of this video, though. The topic of this video I would call limitations of the reaction equation. So right here we have a chemical reaction equation. I've obviously gone ahead and balanced it up. Most of you aren't going to be able to look at this and say where this happens or anything like that, and that's fine. You don't have to. But we can, as Chem 20 students, I would hope, be able to look at all of the reactants and the product here. We could classify it as a formation reaction because we have two elements forming a product. We could see that we have two elements and this is an ionic compound. We could probably even name this ionic compound as iron 3 in brackets oxide. But where does this happen? This is the reaction that forms rust. So in a car, if you have, the paint and the clear coat chipped off and there's a piece of bare metal exposed on a car, you're going to see eventually rust. Particularly in older model cars, although newer model cars, provided they are made they have steel body panels and they're not made out of aluminum or plastic, you're going to see this happen when there's steel or iron involved, mostly because steel is mostly iron. So we look at this reaction, and okay, I take a piece of iron metal and I put it in the air. This is going to be more boring than watching paint dry. The reaction does not really happen unless there's a couple of other things in the mix. Those other things are not in our little reaction here. Like, I only have the reactants and the product. There's a lot of stuff that we're not talking about when we look or when we write down a chemical reaction equation. So the first thing, we assume, like when I give you a reaction and I'm like, so-and-so mixes with this and forms product. And you're like, all right, well, Lorenz gave me this chemical reaction, so I'm going to assume some stuff about it. The first is that the reaction happens at all. It might not. There are certain conditions that have to be met for this particular reaction to happen. The second one is that the reaction goes quickly, at an observable rate. So one reaction that we saw very, very long time ago was this. Lead 2 nitrate plus potassium iodide makes 2 potassium nitrates and a lead 2 iodide. And the interesting thing about this reaction, I showed it to you on a video way at the start of the course, and the reason why I showed you the video is because it looks very cool. It forms a yellow solid, a yellow precipitate. And if you remember that video, or if you look up lead nitrate potassium iodide, you're going to get a video of 2 colorless solutions, and they get mixed together, and boom, they make a yellow solid. And that reaction happens very rapidly. Like, you get to watch the reaction take place. This guy up here, the rusting reaction, yeah, I mean, we do have a lot of time on our hands lately, but I don't think anyone is going to want to spend it sitting around watching a piece of iron metal rust. I mean, if you do, I'm going to look at you weird and think differently of you. But yeah, this reaction just doesn't happen very fast. You can't, if you take a piece of iron metal and you put it on a table, is it going to go and rust right away? No. So the reaction doesn't happen in normal, just if it's in a dry condition. The reaction actually needs more stuff in order to take place. And the last assumption we make is that the reaction goes to completion. We have a nice little single-sided arrow here, and you're going to learn in Chem 30. Yeah, remember I said I'm like a professional liar, like that's my job? Well, in Science 10 and the first 3 quarters of Chem 20, we lied to you about how chemical reactions work. Now, most of it is so we have a bigger selection of reactions to kind of give to you as examples. That's for sure part of it. So I can just dream up an two ionic compounds and just tell you that they do double replacement reaction, and you have to be like, yep, Kähler said so, so there we go. Do we really need to make sure every chemical reaction we use in an example is for sure happens? No. So we assume also that the reaction goes to completion, so it's going to use up one of its reactants. In the case of rusting, yes, provided you give this reaction a long enough time to work, eventually all of the iron metal in your little sample of iron metal will turn into rust. You're obviously not going to use up all the oxygen, because our source of oxygen in this case would be the atmosphere, like the air. But there are a lot of reactions that kind of go and they get stuck. Like they'll go part way and then they'll get stuck. And I think you may know a reaction like that, and I'll give you guys a couple of examples in a second. So what's missing from this reaction? Lots of stuff. In later on chemistry, if you go to like university chem, and even in Chem 30, you might see some additives, some stuff we put over top or beneath the arrow that kind of adjust the arrow and change really what it means. It still means a reaction is going on, but it's going to give you some extra conditions, some things that have to happen for the reaction to work. So what's missing from a reaction? Conditions like pressure and temperature. And down here, there's a reaction arrow with a temperature, which means that whatever reaction, if you put 250 degrees Celsius above it, it means that the reaction isn't gonna really work until the temperature of the reactants is 250 C. If you think about this in terms of kinetic molecular theory, KMT, that makes a lot of sense. You gotta put energy into a reaction. It has to have enough energy to initiate, to start off. What does that mean in KMT? It means the molecules have to be moving fast enough in order to do something. They have to hit each other hard enough. It's like braking when you're playing pool. If you just slowly roll the cue ball towards the racked colored balls and they just touch, you're not going to break those balls apart. They're just going to stay in that little triangle and do nothing. But you really have to crank that cue ball. You have to hit it really hard in order to explode that collection of colored balls. So kinetic energy is movement, and we actually measure it as temperature. Other stuff, the pressure. Yeah, some reactions only take place at a particular pressure. So that's going to be mostly applicable to reactions that occur in the gas phase. So some reactions like the Haber-Bosch process, where we make ammonia, which is this guy right here, 2N2 plus 3H2 equals 2NH3. Super incredibly important reaction. Not necessarily for you as Chem 20 people, But this is the reaction that makes ammonia. And ammonia, this guy right here, is then used to make fertilizer. And fertilizer is what enables human societies to grow staggering amounts of food. So without fertilizer, we'd be in deep trouble. We'd be in global famine. I mean, we wouldn't be able to support this many people to begin with. But anyways, this process requires a certain temperature that I don't remember and a certain pressure that I also don't remember. If you just take nitrogen and hydrogen, say you fill up a balloon with nitrogen and you fill up a balloon with hydrogen and you dump the gas from the balloons into a container and you just sit there, you're gonna die of boredom. Well, you'll die because there won't be any, you won't really be able to spot any ammonia being formed. It won't happen at air pressure and ambient temperature. If you do this at SATP, nothing's gonna happen. The next thing that a reaction equation misses is what's called a mechanism. I'm not going to talk about these hardly at all. This is an example of a mechanism. It shows the structures of the molecules and the ion that we're dealing with. It shows also this middle step, which is usually called an activated complex or a transition state. What that means is it's the in-between between the products and the reactants. So you can see here we have an OH, that's a hydroxide, coming in to this bromoethane molecule. It hits the carbon that's bonded to the bromine, and it forms kind of half bonds with these. And then the bromine takes the negative charge that used to be on Mr. Hydroxide and it pieces out. So it makes a bromide ion. What we've actually done here is we've taken what's called a haloalkane. This is a carbon containing a hydrocarbon with a bromine on it, with a halogen, and turned it into an alcohol. So this is now ethanol. So reactions give us more reaction mechanisms give us more detail about what's going on. It doesn't tell us about how fast the reaction takes place. It doesn't tell us how far the reaction goes. How far the reaction goes is something that we call an equilibrium. Here I've shown you 3 different possible examples. What you might usually, or what you might see, I'm just going to use R for reactants. You may see a double-sided arrow where the arrow pointing towards products is way, way, way bigger. That would tell you that this reaction favors the products. In other words, if you make this reaction happen, it's going to go mostly to the product side. You might have some reactant left over. Then you might have something like this, where the reactant and product arrows are roughly the same size. That would tell me that this reaction it goes some of the way. It doesn't go all the way. So that means you'll still have some reactants that are just sitting there doing nothing. They don't actually turn into product. You'll learn more about that in Chem 30. Obviously, another possibility is the arrow pointing towards reactant. That means that this reaction, it doesn't really want to go. And obviously, if something goes 100% of the way, like a combustion reaction or a precipitation, one that forms a solid, you'll see a lot of the time a single direction arrow. When we do our reactions in Chem 20, we're dealing almost exclusively with single direction arrows. One other thing that I'd want to tell you would be sometimes you get a percentage. And this one is actually something that you might remember from acids and bases. In a strong acid, remember, in modified Arrhenius theory, here's my little L for water liquid. I have my HA, that's my acid, that's aqueous. In a strong acid, literally every single one of the acid molecules reacts with water to form hydronium. So that's a strong acid. But we saw you can also have a possibility with a weak acid. And in a weak acid, we're still making H3O, we're still making a hydronium, and whatever the counter ion is going to be there. We just call it A minus. It can be whatever, it's whatever's left from the acid. And we wrote something like this, less than 100%. That means that not all of this ionizes. So in a strong acid, all of it ionizes to form hydronium and the counter ion. But in a weak acid, only some. This number, you might see, usually for a weak acid in Chem 20, we just say less than 100. There are different percentages, obviously. And here's the other thing. It depends on temperature, and it depends on concentration. These things are not always linear. But anyways, I'm getting off track here. We don't really need to worry about these other than, we know how acids work when they're strong or when they're weak. And it also doesn't include the measurable amounts. This just says, okay, every four atoms of iron are going to combine with 3 molecules of O2 to make 2 Fe2O3s. Great. That doesn't say anything about any measurable amounts. If you're like, all right, I got 80 kilograms of iron here, how much of this Fe2O3 am I going to make? This reaction doesn't tell us directly how to do that. In the next part of the chapter, we're going to talk about how to do that. So, again, limitations. These reaction equations don't tell us what is required beyond the reactants. They don't tell us how fast it works. They don't tell us how it actually works. They don't say how far the reaction goes. And they don't tell us how much of the products and reactants we're going to have. So we're going to start to expand on this now. So I'll see you in the next video.